Good morning, good afternoon, good evening. What time is it? I don't know. I lose track. Will it dissolve in water? And the title of this little video, like dissolves like. What we mean by that is polar solvents dissolve other polar and ionic substances usually, and nonpolar solvents dissolve most nonpolar substances. That doesn't make any sense. Let's go over some examples. We've been harping on you guys since the first semester of this course at some point to memorize your solubility rules. So just again, here they are. We know that ionic compounds are made of positive and negative ions, and those positive and negative ions will often dissociate or break up from each other in the pure salt in aqueous solution. These are all the salts that do dissolve in water. These are the salts that don't dissolve in water. Perhaps we could say, again, that these pairs of, say, perhaps iron hydroxide or copper sulfide or vanadium carbonate or take your pick, aluminum phosphate, those ions are too strong, holding together too strongly for water to pull them apart. But in any case, if you know what the solubility rules say, you know what will force a reaction and what won't force a reaction. But more to the point here, for this video, I want to look at structures. We say water's polar because it has HOH, or it's a lopsided structure, very polar, very lightweight, and able to dissolve other polar substances like alcohols, methanol, or ethanol, or even acetone is polar if you look at the structure. Of course, this also dates back to first semester course where we talked about bonding and geometries. Maybe you forgot what the structure of acetone is, but it's a lopsided molecule with the carbon double bond oxygen. Sort of in the middle. On the other hand, some nonpolar solvents like toluene and hexane and ethers and carbon tetrachloride, if you look at the molecules, they're not lopsided, not polar, and they do not dissolve in water, but they would dissolve in each other. Interesting. Here are some of the structures. Water, of course. An alcohol has an OH group. Acetone has a C double bond O in the middle. Carbon tetrachloride, a symmetric tetrahedron. So that's not polar, and hexane's not polar, and toluene is a little bit polar, you'd think, but the carbons are so heavy that it ends up being kind of a big blob that doesn't dissolve in water very well. As we'll see in just a second, if I could put OH groups, OH, 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 all the way around this benzene ring, that would allow it to dissolve really well in water. But as a big, massive hydrocarbon, and one reason why I chose some tricky examples here is to emphasize it's not always clear cut. We say, will it dissolve in water? We say, well, define dissolving, and it's often not a yes or no answer. It's a mostly not, or yeah, pretty much. What about naphthalene as a hydrocarbon? This little cartoon, space filling model, shows hydrogen golden and carbon blue, which usually carbon is black and hydrogen's white, but whatever. Excuse me. But in any case, would this dissolve in water? Or would it dissolve in some fat or an oily substance a little bit better? Yeah, the answer is not water, because it's not like water at all. It has these heavy carbons and hydrogens surrounding it. But what I really would like to see is some OH groups. If I replaced each of these hydrogens with an OH group, with an oxygen hydrogen, carbon bond to oxygen to hydrogen, that would allow dissolving in water. What about table sugar? Well, duh, table sugar is soluble in water. What feature about the sucrose or table sugar molecule would allow it to dissolve in water? Because all these carbons don't lend themselves too readily to dissolving in water. But the OH, the OH, the OH, 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 and even to a lesser extent the lone pairs on the oxygens attract HOH. They attract water, and so of course sugar is very soluble in water, I don't know if it would be very soluble in fat or not, or in oil. Um, Vitamin C. There's a tricky one. Vitamin C, soluble in water? Well, there's an OH and an OH and an OH and an OH and a couple of oxygens with lone pairs on them. I'm going to say vitamin C is fairly water soluble, even though I have carbon, 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 hydrocarbons that aren't typically soluble in water. I would guess there's enough OH around enough OH, a great enough number of OH groups, hydroxide groups, hydroxyl groups around those to allow the dissolving in water. And indeed, vitamin C doesn't stay in your body very long. It dissolves in the water, and you eliminate it pretty quickly. It might also be a little bit soluble in oils and fats because of the hydrocarbons and the funky ring there, but definitely water soluble. Um, what is this? Oh, vitamin K3. I don't hear that very often. Would it be water soluble? Jeopardy music. No, I don't think so. Look at all the hydrocarbons. I got an oxygen here and an oxygen here. This might make it a little bit polar, like the right hand side, a little bit different than the left hand side. But the real key in my rule of thumb is the hydroxyl groups, OH groups. This would be a little bit polar. That would be attracted to hydrogen sides of water molecules. So maybe a teeny bit, but for the most part, this would be much more soluble in fat than water, for sure. Hexane, we kind of, is this molecule more soluble in hexane or water? It's a nasty insecticide used in the 1980s or 70s, and they stopped using it because it's nasty. See any OH groups around there? No. Chlorine, some heavy chlorine, some heavy carbons, little teeny hydrogens, but those don't count for anything. So definitely not water soluble, definitely fat soluble or oil soluble. What about this molecule? Naphthalene in old-fashioned mothballs. It smells, it's got an odor, it's kind of volatile, but it's a solid at room temperature. Would it dissolve in water? See any OH groups around there? No, I don't think so. So it's not water soluble, it's fat soluble or oil soluble. So some of those other non-polar solvents like carbon tetrachloride or hexane, of course, it would dissolve in that pretty well. Water or hexane for the alcohol. This would be kind of cool. It would definitely dissolve in water. We know alcohols are almost miscible in water, pretty much. At least the small alcohols will dissolve any amount you want in any amount of water. But it might also be fat soluble to some degree because of the hydrocarbon end. So that's, I guess, one cool thing about the small alcohols. They would dissolve in water or fat. Yeah, right, water or oil. Um, yeah, there you go. So small alcohols are miscible in water and miscible in hexane. Interestingly, this methanol this is a cool one. Methanol has a small hydrocarbon component, which makes it slightly soluble in hexane. But by the time you're to ethanol with two carbons and hydrogen surrounding, that allows it to be mixable in any proportion with hexane, and same for water. And that OH group, there's an H hidden in the back of this. I can't see it, but it's there, OH group, and the hydrocarbon group. And the more hydrocarbons you get, the less water soluble it is. Looks like this one's, though, miscible in hexane because of the hydrocarbon portion. That's a nice table. In terms of geometries, don't forget about this. The water's lopsided, and so as negative ions or positive ions enter into solution in the water basically surrounds them because the positive side of the water is attracted to the negative ions, and the negative side of the water molecule is attracted to the positive of the positive ions. And so, I lost my train of thought. Which one's wrong? I think it's, which one it is. Yeah, that's not right, because the positive sodium ion is not attracted to the positive side of the water. That's drawn backwards. Positive sodium would not be attracted to the positive of the water. Or we can ask silly pictures like this. There's so many millions and uncountable trillions of water molecules. Usually we'll leave some of them out for simplicity. But if my positive side of the water is attracted to the negative ion, and the negative side of water is attracted to the positive ion, I wonder what this could possibly be. Negative, positive, positive, negative. Yeah, that's it. So looks like the ammonium being positive is probably attracted to the negative side of the water, and the nitride, this probably would dissolve in water to some degree, at least all ammonium salts dissolve in the water. That's a tricky one. Let's do another tricky one. Go ahead and pause the video now if you want to try this on yourself. What salt would this be? And if you don't want to pause the video, here's the answer. The positive ion attracted to the negative part of the water, or the negative ion attracted to the positive side of the water. Which polyatomic anion do I have to choose from that looks like it has one central and three surrounding oxygens? Probably carbonate? I choose, yeah, aluminum carbonate looks pretty good, especially in terms of the ratios of the two positive aluminums to three negative carbonates. Interesting enough. Here's another one if you feel like it. If you want to pause the video, go for it. Don't look at the answer. Cool. Which one is this? Looks like the positive of the water is attracted to the blue negative. So I got three simple atomic anions and 1, 2, 3 black simple one ion cations attracted to the negative water. Wouldn't that be a 1-to-1 ratio? One black to one blue? Aluminum nitride. Guys, thanks for watching, and I appreciate your time and good luck in your studies. See you in class.